Hi, and welcome to this session. During the next hour or so, we're going to go through the latest innovation Cisco has been working on in terms of integration with Hashicorp products, in particular, Consul and Terraform. So my name is Nick Vermandi, and I'm a technical marketing engineer with the Cisco Data Center Group, where I focus on everything around open source and container. So in the context of this talk, I'm going to focus on the integration we have done with our SDN solution for data center, which is ACI. And I'm going to explain, maybe for people who are not aware of what ACI really is, the concept behind it. So let's take a look at the agenda for today. First, we are going to take a look at the current state of the data center in terms of software and hardware stack and see how new ways of delivering application has affected how people operate data center, especially in terms of cloud native adoption. There's a lot of new tools that are surrounding those concepts for developers, but also for people from the infrastructure. And this has some impact also on vendors such as Cisco in terms of not only delivering new hardware and software capabilities, but also bringing people up to date in terms of automation and DevOps tools, thanks to initiatives such as Cisco DevNet, for example. Then we'll focus on Cisco ACI and see how a model-driven network can really help with API adoption and also with the integration of infrastructure as code tools such as Terraform. And in this section, we'll have a quick demo to show you how with ACI and Terraform, you can quickly leverage a single language, declarative language, to deploy and control the lifecycle of your workloads, both on premises, but also in the cloud, in AWS in this demo. Then we'll continue with another aspect, which is also very important around networking visibility and policy management. In this context, it will be the integration of ACI and Consul. ACI as a network can provide a lot of visibility in terms of the endpoint you connect to it. But obviously what is missing is the application element, application component in terms of the services that are running on those endpoints. This is where the integration is very useful. And we're going to also see a demo of ACI and Consul on those visibility aspects. So let's get started. In order to understand the current challenges that networking is facing within the data center, it's important to take some step back and take a look at what was the different transition in the data center. So it's been quite a journey where a lot of innovation happened by adding abstraction to the technology that was already existing. So if you take the example of compute, then one of the major transition of the last 20 years was really virtualization and having the ability to consolidate and abstract compute resources for cost saving. Or one of the other argument at this stage was green IT and concept around those lines. Then, of course, because the compute part of the data center had tremendous advantages over other areas such as networking, there was some requirements for new capabilities when delivering services to those compute units, right? So typically when you were spinning up a VM, you had to ask or to wait for the network team to give you VLANs, a subnet, all those kind of things. So there was a lack of flexibility for the network when deploying new workloads within your data center. So this is why concepts such as SDN were very popular and are still very popular because it allows the compute layer and the network layer to be aligned together to provide the same level of flexibility when it comes to workload management and network lifecycle management together. So these changes have been mainly driven by infrastructure requirements, but how about the application? So in the world of application, there was always this waterfall methodology, which was a sequential way of developing application, as opposed to the agile model, which is more an iterative way of managing software lifecycle. And because of this iteration, it requires a faster release cycle. And this is why Docker had such a big impact, because with this technology, it was suddenly possible to very quickly package software into immutable images and ship them anywhere in the world, and enabling more efficient collaboration between developers. I mean, containers was not something new. We had a couple of technology related to containers, such as edXC or Solaris zones, for example. What was not there is an ecosystem of tools to facilitate their utilization. So the Docker CLI is a great example of these tool sets that enable developers to manage their environment a lot more efficiently, but it was more of a desktop technology. When it comes to integrating this technology within the data center for scalability reason, there are a lot of other factors to consider, such as clustering, multi-node, scheduling, things like resiliency and high availability were not there as part of the original Docker client. And the industry basically went more into the Kubernetes direction, which was provided by Google at the beginning. And if you look at those various technologies, so virtualization was abstracting compute, SDN was abstracting networking, bringing a vehicle for your application code. And Kubernetes is basically taking all those notions and bringing them into a single data center scheduler. So now we really have all those concepts brought into a single technology, which has a huge impact on network, because obviously there is a SDN component to Kubernetes. So the consequence of all these transitions is that our data centers are running a lot of heterogeneous technologies that bring concern for the enterprise around operational consistency, security, how to operate multi-location data center when it also has a cloud component to it. And in parallel to this, the application architecture has also changed, and we're going to see how it also has some impact on the network. So back in the days, we used to have a monolithic approach where a single application was basically a set of services running on the same machine, whether a bare metal server or a VM. But with the advent of microservices, then the concept is to have a much more dispersed model where every piece of the application is running as an independent service accessible through API, which obviously leads to a larger number of endpoints connected to the network, but also bring another layer of policy requirement, because it became a lot more difficult to identify what services are running where. This is why service discovery is really a key component within those modern environments. And if we look at even more recent way of composing applications, there is a trend to use even more granular calls, which bring concepts such as serverless, which is event-driven to execute a piece of code on demand. But I would say that this is still the early days of serverless, and that today most of those serverless services are consuming public cloud as opposed to within the data center. So for this new applications architecture, the concern is more around how to determine how very dynamic services can talk between each others and how the network should react to it as we move down the layers of the OSI model. Because if we define application policies more focused on layer 7, how about the security and the connectivity policies at my layer 3, for example? What should be the new patterns to respond to this new requirements? So at Cisco, we believe in a networking model with security and connectivity policies at every level, and it tends to resonate well with our customers. And this is why it is so important to have integration with tools such as Consul that allows application policy to also apply security between services, regardless of the form factor of the workload. So let me go back for one moment on the topic of infrastructure as opposed to application. So remember I told you, the first set of transition we had was more related to infrastructure requirement. There was a lot of innovations, but in terms of the hardware, did we evolve that much? If you look at what is still sitting in our data center physically, I mean, you still have boxes, right? Servers. You still have storage boxes as well. Now we may have network fabric as opposed to three-tier model architecture, but it's more or less still physical boxes with a connected network. And on top of that, we have our application that is running. And this is why we are running data centers, is to be able to run those applications. But the difference is that now those components are usually merged into software stack. So what I mean by that is there is a notion of commodity hardware and scale out hardware for all those components. If something fails, you should be able to replace it very easily and at a low cost. And this brings more value to the software, of course. This is one of the reasons we built ACI, to associate first-class hardware with a software that can adapt to all the environment and technologies we've mentioned so far. Another relevant question often asked by customer is, how about automation? Does this new technologies and cloud native adoption bring new automation solution or principle? And the answer is yes. And a good example is Kubernetes operators, which allows you to extend the Kubernetes APIs to create your own objects or custom resource definitions. Then you can watch and monitor the API to detect any changes on those objects and act upon those changes. So for example, if an object is created in the Kubernetes API, it may trigger in your logic the creation of Kubernetes objects such as pod services, config map modification, etc. But another use case is to apply more generic automations to it. So to be able to react to a change into your Kubernetes manifest, then you can trigger some automation. So it can be things like Ansible or Terraform. There's also a project called Terraform Kate that allows you to run Terraform plans essentially. So you will have probably guessed where I'm going with this, right? By combining a Terraform operator with an ACI operator, which you have an example here for our SourceNet features inside Kubernetes. By combining those operators, you end up with a very versatile automation solution. So now to understand why a service discovery is really important within a modern network, let's take a look at the Kubernetes networking concepts, such as service communication. So by default, a container or pods in Kubernetes, they can be grouped as services, and those services can talk to each other within the cluster, but by default they cannot talk to the outside, and the outside cannot reach them. That is the default Kubernetes configuration, and when a service needs to talk to another service, then every node runs kube proxy that will act as a load balancing mechanism to redirect to the required pods in the backend. There's also an implementation of native security using Kubernetes objects, which are called network policies, and allows you to create network security rules between services and limit the communication on specific ports. These features are available within a cluster, but when you have to cross the cluster boundary, then you have to find other solutions. This is where solutions such as Consul Connect can be very useful, because it allows you to make services between clusters talk to each other and create the security policies in a single place. So on the one side, we have service identification as well as security policies for Kubernetes cluster that is also valid for virtual machines. And on the networking side with ACI, we also make containers first-class citizen as well as virtual machines for end-to-end visibility on the network, which means that now by associating ACI together with Consul Connect, we can have end-to-end information, including networking and also application details. So far, we've been talking about on-premises solution and also challenges, but what about the public cloud? So in public cloud now, customers are not only consuming EC2 services, for example, in AWS, where you just deploy virtual instances. There are other services that are very popular, such as AWS Lambda for serverless, or services related to machine learning and artificial intelligence, because you can instantly take advantage of AWS resources, hardware resources, compute power at the fraction of the cost. So all these services also come with networking and security requirements. And then when you scale them, it can become an issue for enterprises. And to be able to maintain a consistent compliance across the board, then those notions often fall back into traditional network and security teams' responsibility. Typically, these teams don't have advanced knowledge of cloud concept, including network and security, which are very specific depending on your cloud provider. So what they need to be able to operate those hybrid environments very efficiently is a common framework they can use both on premises and in public clouds to maintain a consistent layer around security and networking. And this, of course, include automation of those aspects. So now GitOps and all the cloud native tools are not only reserved for developer, because those tools can lay out a common framework across various environments. And because infrastructure as code provides so many benefits, it's very common for this infrastructure team to start utilizing them. When you go to a public cloud, of course, it comes with the battery and all the tool sets, but this is not necessarily what people want to use in that case. So now I repeated already several times, but it's worth saying it again. In order to deploy a common framework for hybrid cloud, Terraform, Consul together with ACI provide tremendous benefits. And now I'm going to focus a little bit on ACI to explain you what are the capabilities and why it works so well when associated with Hashicorp tools such as Terraform and Consul. So the idea of ACI is to build a single overlay across heterogeneous environment running different technologies. So whether running your on-premises data center on ACI hardware, so Nexus 9000 switches, or running Azure workloads or AWS or Google in the future, as it is a roadmap item, you use a single language to define how endpoints can talk to each other by using contracts, regardless of the form factor and the location of the workloads. So that means that whether you deploy a containerized solution or VMs in the cloud or vSphere virtual machines, or of course bare metal server, you use a single framework, a single API to enforce networking and security policies. On top of that, ACI is a model-driven technology, which means that you don't and you never interact with the low-end systems, which are the switches in our case, or the AWS API in the case of AWS Cloud, for example. you only talk to a centralized controller that in turn will translate policies into the relevant language understood by the backend systems. So you can think of ACI as a network API and a generic translator for network and security policies. Another roadmap item worth mentioning would be the ability for ACI to manage security policies for any type of native service in AWS, so not only EC2 instances. What is quite unique about ACI is that it normalizes the overlay for any type of workload, which means that for every endpoint you connect to that network, all the network information will be available. Things like IP address, MAC address, traffic flow, packet drops, counters, etc. ACI makes it available via APIs. So every integration you build on top of ACI will also be able to leverage this normalized information. This is why one of the use cases we often see with our customers is the creation of monitoring systems, basically on top of the ACI APIs, using its database as a central point for network health information. So over time, ACI evolved from a single data center solution to a multi-location architecture where every individual site can operate as a separate fabric. So those sites can be on premises, of course, and can be also a cloud provider. And if you need to synchronize the policies and create connectivity and security policies between elements located in these various sites, then you use our ACI multi-site orchestrator, which is acting as a federation entity to provide a single policy language for all your connected networks. So in terms of the policy itself, ACI use multiple concepts. So the first one is called EPG, or endpoint group, which groups endpoints together into a security object that you could compare to a security group in AWS, for example. So depending on where you deploy those endpoint group or EPGs, they can be rendered differently. So for example, if you use a bare metal server, your EPG will be defined by the VLAN, but you can also place virtual machines in the same EPG, and it will be defined by the vCenter integration. In the case of containers, you can map namespace to EPG. And for the cloud use case, there is one mapping that is pretty obvious, which is EPGs to security groups. By default, ACI is a whitelist model, so EPGs cannot talk to other EPGs unless you create special rules or access control lists that we call contract in ACI. And those contracts will define how those endpoint groups can talk together, on what ports and what protocols. All those objects are configurable in APIC, which is our controller, and these configuration elements are exposed via APIs. ACI represents its objects as a management information tree, and it's entirely accessible through RESTful APIs. All the configuration elements, as well as health attributes and counters, are represented as objects as well. And all of these managed objects, or MOs, are identifiable by their unique name. Another important aspect of the ACI object model is that explicit relationships may exist between different branches of the tree, such as here between application and virtual network and VLAN, for example. So those dependencies are really well represented in Terraform because fundamentally the foundation of Terraform is based on a cyclic graph to represent the dependencies between the resources. So the example on the slide here illustrates the use case where an admin needs to attach a virtual machine, let's say a vSphere virtual machine, to an existing ACI EPG. So you can see that an EPG is depending on an application network profile, which itself also depends on a tenant. Another example would be in the cloud. by using the same ACI provider, as I mentioned before, it's a single language, so single provider, whether you run ACI on-prem or in AWS. So it's the same kind of use case where you have the sysadmin who wants to deploy an EC2 instance and attach it to an ACI EPG. Obviously, in the cloud, we don't use any ACI hardware. There's no Nexus 9K or anything, but we have our Cloud APIC version that resides in a dedicated VPC and that can translate all the ACI, let's say, vocabulary into AWS native language. And the AWS native objects are also represented in the Cloud APIC object model this time. So now, let's see some code maybe to illustrate this example where we're going to be deploying ACI configuration on-prem as well as an instance in EC2 that we are going to attach to a new security group. So for this first demo, we are going to use the ACI Terraform provider to orchestrate two workflows, one which will be within AWS for the creation of a new application, and this application will be called DevApp as displayed here. It will be composed of two EPG, one EPG called Web Services, where we are going to attach the EC2 instance, and what we call an external EPG that will be representing the internet essentially. And we are going to create a contract so that web services can talk to the internet in that particular direction. So web services as source and the internet as destination. And we're going to see here that if everything goes well, we will have the corresponding security groups that will be created, one for the web services and one for the internet. As part of the same Terraform plan, still using the ACI Terraform provider, we are going to instantiate a new tenant, but this time within the physical fabric on premises, and basically create the same sort of topology where we will have an application network profile called demo app on-prem, this case, with a DB EPG. And the goal here will be to associate that DB EPG with a particular physical port on a switch. So in our case, the switch will be the switch 101 and the port will be 123. So you will notice that we will be talking to both Cloud APIC in AWS and to our physical APIC on-prem. And this is because we don't need to sync the policies between both environments. So for example, I don't need my DB to talk to my EPG web services in the cloud. If your use case includes this scenario, then of course you would have to use our multi-site orchestrator to orchestrate the policies across multiple sites. But that's not the purpose of this demo. And we recently released a Terraform provider for our multi-site orchestrator, which will be part of another video. So let's get started with the demo. So this is our Terraform coding environment here with VSC. And as I was saying before, we use a single Terraform plan to cover both AWS and the on-prem use cases. We achieve this by creating two instances of the ACI provider. You can notice here that there is one with an alias, which is CAPIC, and one which doesn't have any alias created. So the one without alias will be the one we use for on-prem, which means that when resource won't have any special tag, it will use the default provider, which is the one related to our on-prem scenario. That also means that all the resources, which will include the reference to the CAPIC alias, will use that particular provider instance for cloud provisioning. So if you look at the result that we are going to create, we're going to start with on-prem here. There's no alias reference by these resources, which means that we will be using the on-prem provider instance. So for the on-prem workflow here, we're going to start by creating an ACI tenant, then an application network profile called demo app on-prem, Then we'll follow up with the creation of an EPG. And in that case, we are going to deploy that EPG on a physical port on a specific VLAN. This is why we need a reference to what we call a physical domain in ACI. And you want to specify a data source there and not a resource, because we need read-only access so that when you destroy the Terraform plan, you effectively don't destroy the physical domain entirely. Then we'll create a static path, which will define what port needs to be associated with that EPG. In our case, it will be port 123, and we want to program that EPG with VLAN 1100. And that's it for the on-prem workflow. Now you can see the remaining part of the Terraform plan. Every resource we create will have provider equal ACI.capic, which references the alias we have created before for the second provider instance. Then the first thing we're going to do is declare here a data source to represent the common tenant, because we will need a filter that is in here to attach to our contract. So the filter in the contract will just specify the rule set to allow traffic. In our case, we will use the default filter, which is basically any permit. But for that, we need the reference to the common tenant. And again, because you don't want to delete the common tenant upon Terraform destroy, you want to make it a data source as opposed to a resource. Then we follow up with other resources that are particular to the Cloud API configuration. In particular, we need a cloud context profile, which is mapping our VRF with our CIDR, also including the region where we want to deploy our VPC. Next comes the creation of our ACI VRF within AWS. So you will notice that ACI VRF is the same object whether you are on-prem or in the cloud. So all objects with ACI Cloud prefix are really specific to Cloud API. Then we'll create our CIDR Cloud Subnet where we want to attach it in what availability zone. And then the remaining part will be for our application creation. So we will start with the cloud application, then the contract, and the filter. You will notice again, we will use the filter that is in the common tenant. So this is where we create the interpolation that references the data source for the common tenant we just have created before. Then the contract subject. And finally, we're going to end up by creating the cloud EPG we want in that tenant, associated with the VRF and the cloud application we have previously created. Then we need a cloud endpoint selector so that we can classify EC2 instances in that particular EPG. And there are multiple criteria you can use. In our case, we're going to be using a tag. So that means that all the EC2 instances matching a specific tag will be classified as part of this cloud endpoint group, which is quite neat because it allows us to dynamically associate security group with EC2 instances just by adding tag to them. Finally, we need to represent the internet, and you can do that by creating a cloud external EPG. And in the same way, you have to classify EC2 instances into Cloud EPG. We have to classify the traffic into an external EPG, this time by matching specific IP addresses or IP prefix. In our case, this will be the wildcard 0.0.0.0/0 to classify internet traffic as external EPG. So before applying the Terraform plan here, let's just quickly check that the AWS configuration is completely empty. So we can see that we don't have any VPC in US West 1 other than the default one. And similarly, let's just check the current status of the security groups. Yeah, we don't have any special Cloud API managed security group yet. So now we are ready to run the Terraform plan, but before, let's just check that the state file is empty. So Terraform state and then list. Okay, we have nothing. So now I've also added the console of EC2. And you can see that there is no running instances. The only one that is there is terminated, which was from my previous test. Let's run Terraform plan now. So 18 resources are going to be created, and there is nothing really special there. It just contains all, so first the data source that we are going to read, and then all the resources detailed that are going to be provisioned both on-prem and in Cloud ACI. Okay, now we're good to go. Let's apply the Terraform plan. I'm also going to refresh the EC2 console. You can see that the instance is initializing now. So now, before checking directly the security groups in the AWS, let's quickly check the Cloud API configuration. So this is our Cloud API dashboard. What we want to verify is that a new tenant has been created. It is there, AWS Terraform 10. Then if we focus on that tenant in the topology section, let's display the VRF, maybe the region. You can see that a new VPC has been created corresponding to our VRF, and that it is located in US West 1. And we have a single cloud application profile, which is the dev app. Now, if we double click in this application and go to topology, let's display contracts and security group. You will see that, as expected, I have one external EPG, one web services EPG, two security group that has been created, and the contract has been attached to my EPGs. If you go into application management, then you will see those two EPGs, as well as provided contract from the external EPG and consume contract from the web services. And this contract is the allow internet that we have created. And we can see that the filter that we are using is coming from the common tenant. Okay, so in cloud resources, you can also see the AWS specific resources, such as the security group I was mentioning. You will have the cloud provider ID, which is the security group ID as displayed in AWS, and various information here. So now let's check the corresponding information on AWS. So we have our instance there. And if you look at the security group that you find here, you can see that it's Cloud EPG-Web Services. And in by rule, this is basically I am able to talk to myself, security group as source and destination. And outbound rule, this is where we should see something more here. You can see destination. This is the wildcard I had mentioned in the Terraform plan. In terms of the tag, you can see that we have the one we have specified in the Terraform plan, which is type equal UAT. So remember that one. Now let's double check the classification in ACI. So if you go back to the EPG and you double click on the web services, here you will see that the endpoint selector here is type equal UAT as the key value pair. You can see that you have one endpoint that is currently classified as a member, and this is the EC2 instance we just deployed. Now finally, just take a look at the security group. You can see that we have a couple of security groups there. The one we are interested in is that one, the Cloud EPG Web Services. Then again, we can display the inbound rules and the outbound rules, and this one has been added by Cloud API. For the last part of our verifications, I've added the APIC view on the top here, but I'm not going to use the APIC UI to double check what has been created on premises. Rather, I'm going to use just Terraform commands. First of all, let's list the resources that have been created. And let's display some of the on-prem resources. Let's start with the application profile. Okay, we have all the information about that application profile as we would see on APIC itself. So you don't have to connect to APIC every time. Once you have deployed infrastructure with Terraform, you can just use a view of your state file to monitor your environment, provided that no one manually modifies what you have created with Terraform. Finally, let's check the state of our static path for the VLAN configuration. Okay, we can see that effectively VLAN 1100 has been programmed on ACI. And some of the parameters displayed there are the one by default. And finally, we can see also that the port 123 has been programmed with that VLAN. That concludes our first demo. Now that we have deployed infrastructure components with Terraform, let's talk a little bit about the services that run on top. If we take ACI and Consul as individual solutions, on the one side, Consul provides detailed information for application services and service health. ACI on its own provides deep insight into the network. And we've seen that regardless of the type of network, it can normalize the information for end-to-end visibility. So individually, they are missing a piece of the information. Consul doesn't have the full picture of the network, and ACI doesn't have the full picture in terms of the application. So when you conflate those two solutions, you can basically solve any application issue you may experience. And as ACI takes advantage of assurance solutions such as Cisco ACI, it can directly benefit the application developers or the platform teams in terms of application uptime and high availability. Multiple use cases can be derived from this. So for example, with the advent of the NetOps philosophy, security becomes a very important role, and for efficient security, the network needs to be able to react to dynamic changes. So even in the context of networking, service information is paramount. This is where service mesh can bring a lot of benefits, especially in the case of Consul Connect, as it supports any type of form factor and provide gateways to talk between Kubernetes cluster, for example. Another use case is policy instrumentation. With recent innovations, network tend to happen as a side effect of the application policy. Therefore, it makes sense for the application tools to inform the network about what needs to be open, especially if we think in terms of whitelist network, where by default no communication is allowed unless explicitly requested by an application policy, for example. So essentially, it would allow the network to open connections on demand. As a result, the first phase of the ACI and Consul application focuses on service visibility and health. The second phase would be providing more capabilities at the policy layer. So you can download this application from the Cisco ACI App Center website. It's currently in beta, and now in the next couple of minutes, I'm going to walk you through a quick demo of the app. So I am connected to one of my APIC here, and let's go to the Consul tenant, which is hosting the Kubernetes cluster. So as I was saying, I have the container networking layer that is provided by ACI. What that means quickly is that we have a containers domain integration providing visibility on the Kubernetes environment. So all the different nodes, master, namespaces, the services, deployments, replica set, and pods. So we really have full visibility on the cluster. Therefore, we can get information on the pods. For example, here I've got a replica set. Here it's composed of a single pod, and it's got this IP address, this MAC address. So we can see it directly as an endpoint connected to the fabric. Even though it's running in its own overlay, software overlay, it's still terminated and normalized at the top of rack switch. This means that ACI can now correlate this endpoint information with console information via the app. So let's go back to the tenant. The console app is available in the tenant view. Here we go. So this is our dashboard. You can see that we have currently 14 service endpoints connected and 22 non-service endpoints. Non-service endpoints mean that there is no console agent installed. So now let's take a look at the operations view. We can see that we have one data center, DC1, and then there is a bunch of fields that are displayed for every endpoint. So in our case here, every endpoint is a container. We have consolidated information here between ACI and Consul. So for every endpoint, we have its name, its IP address, its application profile, name of the EPG, the health reported by ACI, and then we have information from Consul, such as Consul node name, node checks, service instance, and port ID. We can also have a more graphical view displaying the ACI hierarchy. So from the top, we have our application network profile, then we have the EPG. Then as a child, we have all the endpoints, and attached to every endpoint, we have the console information, which comprises the service name, the address, and the port, as well as service checks and relevant service tags. So for example, here for our web container, we have even more information, such as the physical interface it's attached to, and the latest status of the node checks. Then the last part is service intentions, but as displayed here, this will be a roadmap feature. In this demo, we've seen that ACI and Consul can provide application visibility and service awareness in Kubernetes environment. In addition, as ACI can mix all types of form factors into the same tenant, the same capabilities are available across any type of workloads and any location, including public cloud. So to sum it up, we've talked about data center automation frameworks, highlighting that your favorite cloud tools are being used for on-prem too. This is usually challenging because APIs are not the same on-prem and in the cloud. However, Terraform and ACI provide the right level of abstraction to accommodate many hybrid cloud use cases by providing a declarative language and an abstracted framework. Finally, Consul and ACI enable a powerful solution for end-to-end application deployment and monitoring, as well as policy discovery and management. Again, thank you very much for joining the session. This is now time for Q&A.